Hello everyone, today we're going to be talking about voltage, Kirchhoff voltage law, and Ohm's law. We're going to be talking about voltage because I'm going to be talking about how I do plus or minuses in my KVL equations. This may or may not go against what you learned already in physics and other engineering courses, what have you. I'm focusing in this manner because that's what I need to do for these YouTube videos for this class that I teach at a school. All right, so let's go into this. First and foremost, when you think of voltages in a KVL or in a loop of a circuit, think of going up and down mountains. So for the purpose of this YouTube series, think of the positive terminal as the top of a mountain. Think of the negative terminal as the bottom of a mountain, okay? Now, when you go up a mountain, you are putting in energy, you're putting in work, you're putting in voltage into your system, into the system of going up the mountain. When you are going down a mountain, you are going to be experiencing energy leaving. That's why you often want to run fast or even walk faster when you go down a mountain. So in our KVL equations from here on forth, the way I like to explain things, if you go up from bottom to the top of a voltage mountain, then it's positive Vx in the KVL equation. If you are going down or from positive to negative in a loop, then that is negative Vx in the KVL equation. Cool? Now, let's do an example. Let's say we have this circuit provided to us. And the question being asked is, what is the KVL equation for this circuit? Okay, and a little review. KVL is the summation of voltages in a loop is equal to 0 volts. So to do this problem, steps. First, what are we solving for? KVL equation of circuit. This has no units. Second, what concept should we be using? KVL. Summation of voltages in a loop is equal to 0. 0 volts. Now, how do I do this? The direction of current or the direction of our journey has not been drawn. So for shits and giggles, let's assume it's clockwise. So if it is clockwise, then I'm going up Vs, down Vx. I'm going minus to plus, plus to minus. Ta-da! That is a KVL equation of this loop. I'm going to mention that this is clockwise. What if it was the opposite? What if it was counterclockwise? If it was counterclockwise, then you'd be going up Vx minus Vs. If you wanted to do Vs first, it's still minus Vs plus Vx. So this would be equal to 0 volts. This is if you go counterclockwise. Okay? Now, regardless of which direction you went, Vx is still equal to Vs. Cool? So, when you have two elements in parallel, the voltages are equal to each other. That's what we just proved here. And I wanted to prove that if your direction changes, KVL will still come down to the same simplified answer. That's what I'm trying to show here. Okay, that's all I have to say about that. Let's erase this. All right, Ohm's law. Now, what can I say about Ohm's law? A lot, especially about how it's taught at the school that I go to. So Ohm's law. Ohm's law is used to what? Used when wanting, that's terrible. When wanting to know the voltage drop across a resistor. Sorry for the terrible handwriting. All right, so voltage drop is used when you want to know Ohm's law is used when you want to know the voltage drop across a resistor, okay? So one way to use Ohm's law is drawn as such, plus minus VR. Let's say current is going down. Ohm's law states that VR is equal to I subscript R times R. And this is why it would be a plus. Okay, so it's plus. Just going to erase it. The plus is imaginarily there. Now, this is how much voltage has dropped across the resistor, okay? Or consumed by the resistor. You may be saying, hold up, Mr. C, why don't you have a minus sign if you're going down a hill? Because right now, I'm not talking about a journey through mountains. Right now, I'm just talking about how much voltage drop was there in across this resistor. So I'm not asking you to consider your journey. I'm just asking you, what was the height of the mountain? That's it. The height of the mountain, the amount of voltage that was consumed by the resistor, the amount of voltage that was dropped across this resistor was blah. Positive IR times R. Whether IR is negative, I don't care for now. When we do all these signs, again, don't forget that it's just algebra. We're assuming that things are positive, and we're assuming current is in fact moving in this direction. It may be the case that current is not, and that might confuse students. So I don't want to talk a lot about that. I just want to say this notation right here is discussing the voltage drop across a resistor, aka what is the height of the voltage across this resistor. That's it. We're not talking about plus or minuses along a journey. We're just talking about what is the height, what is the voltage drop across this resistor when it is drawn in this manner. Okay? So, looking at my notes here. For example, if we come up, let's just say that we switched this box to resistor. Call this R, and let's say IR was going this way. Then our math already shows that the voltage across this resistor is what? Vs. We already showed that, right? Which kind of makes sense. Think about a battery going into a remote. Let's say this is my remote control. So if a battery goes into my remote control, the total voltage drop across my remote is equal to the battery. That's why you put batteries in your remote controls, right? The battery is providing the voltage to the remote. The remote is consuming voltage. So if someone asks you, hey, what's the voltage across the remote control? It's whatever the voltage of the battery is, which is going to be a positive number in this example. Now, students might be freaking out because they're like, hey, I've seen in my school this notation where current is going up. And I want to tell you, that's not used in practice at companies, Texas Instruments, Apple, Medtronic, wherever. I'm just listing where I've interned. So to prove it's not used there. This is hardly used. Why is it hardly used? Because in this drawing, VR is equal to negative IR times R. If someone gave you this drawing right here and they said, what is VR? You will be saying the height of a mountain is negative. That automatically should grind your gears, because no one says, oh, I hiked a mountain that was negative 200 feet high. That doesn't make sense, right? Again, do not confuse this voltage drop idea with my KVL plus or minuses. We are not taking a journey here. We're just answering the question, how high was your mountain? That's this above drawing, 200 feet high. Cool, that's the voltage drop across the resistor. That's the height of the voltage across the resistor. In this one, it doesn't make sense that current is going up, because then you have a negative number of the mathematics, whoever decided to have Ohm's law drawn like this. And so you would be saying the height of my mountain is negative, or the voltage drop across my resistor is negative, which doesn't make sense because there is no negative voltage drop across a resistor. So even though we are teaching you this, it's hardly used in practice. That's all I want to say. If you have any other questions, shoot me an email if you have access to my email. Okay, what else did I want to teach? Let's do an example of Kirchhoff voltage law. Kirchhoff's voltage law. So here's an example. Let's say this is Vs. You have R1, you have R2, you have R3, and let's say the terminals are drawn for us. What is the KVL equation of circuit? That's our question. Okay. I like to do clockwise. I always like to do clockwise for all my KVLs, unless otherwise specified, and we'll go over that in a little bit. And that's if actually we don't need to say that. The only reason I will ever go counterclockwise is because someone in the homework or exam put a current going counterclockwise. That's not in this example. There's no current direction shown. I get to choose my journey. It's 2022. So I want to go clockwise. Okay? So if I'm going clockwise, keeping that in mind, trying to find the KVL equation, no units. KVL says that the summation of voltages in a loop is equal to 0 volts. So if we're going clockwise, that's going to be plus Vs minus VR1 minus VR2 minus VR3 equals 0 volts. The subscripts are being very specific as to what element I'm talking about, and the V represents voltage. Okay? So let me just draw that I have gone clockwise. Okay, I'm going to call it I1. Now, for some reason, let's say I wanted to bring this down even further, and I want to start seeing currents and resistors, algebraic expressions. We could do that. Vs is Vs minus I1 times R using Ohm's law minus I1 times R2 minus I1 times R3. All of this equal to 0 volts. If you zoom into this beautiful drawing, current is going in the positive, leaving the minus, which Ohm's law says VR is equal to IR for that specific drawing, right? Shown here. So if you look at this drawing, current is going in the positive, leaving the minus. And it happens to be in this KVL approach, you can in fact use my mountain idea, because you're going down the R1 mountain, you're going down the R2 mountain, you're going down the R3 mountain, right? So this KVL equation can be deduced by using what I taught you from Ohm's law and from what I taught you about how to go up and down mountains in a KVL journey. Okay, that's the whole point of this video. So, devil's advocate. This is all if I1 is clockwise. What if I1 is counterclockwise? So now green is now representing the counterclockwise. So we're going to have to zoom out a little bit. Counterclockwise. Following the same steps. We're solving for the KVL equation of the circuit. We're going to be using KVL. I'm going to skip that. Let's do the KVL. So I'm going to start with Vs. I'm going down Vs minus Vs. I'm going up R3 plus VR3. I'm still using my voltage mountain journey analogy. That's why I put plus VR3. I'm going up R2, so that's plus VR2, and I'm going up R1, that's plus VR1. All of this is equal to 0 volts. Do you see how this equation is similar to this equation? If you multiply, let's call equation 1 by -1, you will get equation 2. So, to answer your question, what I'm trying to show here is, it doesn't matter which way you decide to go, clockwise or counterclockwise. Because when you complete the problem, you will be able to get the same answer. Let me show you. If we go back to equation 1, we did one step. Now let's just finish it. Vs is equal to I1 R1 plus I1 R2 plus I1 R3. Let's go to equation 2. Minus Vs plus I1 R3 plus I1 R2 plus I1 R3 equal to 0 volts. I'm just using Ohm's law, where VR3 is equal to I1 times R3. That's all I'm plugging in. I don't have to look at the drawing. I just know VR3 is I1 times R3. And then if you put Vs on the other side, you're going to get I1 R3 plus I1 R2 plus I1 R1 is all equal to Vs. As you can see, this is equal to this. So it doesn't really matter which way you want to go, counterclockwise, clockwise. Doesn't matter. But the terminals do. Terminals matter. All right, so that's all you need to know for this video, where I go over voltage, Kirchhoff voltage law, and Ohm's law. Again, Ohm's law is specifically when you were analyzing the voltage drop across a resistor, but KVL is when you care about the journey of up or down mountains, and that is how you have the plus or minuses. Okay? If you have any questions, email me if you have access to my email. Thank you very much.